Guys, last time we talked about the four quantum numbers: the principal quantum number, the energy shells, and the angular quantum number, like the shape. These are the quantum numbers that we're going to be using today. For today, we're going to be ignoring the the spin direction and the orientation. So we're just going to be focusing on these two numbers. So today we're going to be talking about electron configuration. This is a weird graph that looks very fancy, and but really it's quite simple, and you will find it extremely useful. Every time in tests, the first thing I do is on my periodic table, I will draw one of these, so that I can quickly refer to it later. So this n equals 1 means on the first energy level. So last time we discussed how an atom can have multiple energy levels. Technically it can have an infinite amount, but we consider it to be for another atom after the seventh energy level. Here we have energy level equals 8. I don't exactly know why, but still, like I said, by theory an atom can have infinite energy shells. So yeah, seldom we normally won't be needing these, since the periodic table only has currently up to 118. It only has 7 periods, and each period means one energy level, but we'll get more into that in the next slide. But to make this look beautiful and to have practical uses, this is not used for sixth grade chemistry. I'm not sure, but I think this is for later some nuclear reactions or something. But for now, we can ignore the 8s thing. Okay, these are the energy levels. For example, actually let me draw the nucleus as well. N equals 1 is going to be this one, n equals 2 is going to be this one, n equals 3 is going to be this one, n equals 4, 5, 6, 7, etc. So just as a bit of review. Now for the angular quantum number, like the shape. Last time we talked about, 4 shapes: the S, P, D, and F. These 4 shapes. S is a sphere, P is like a bow tie shape, D is a bit like 2 P's together, and F is just complicated. Okay, so now 1S, basically what it means is it has one subshell on the first energy shell, as shown in this picture. The first energy shell is one subshell, second 2, third 3, and so on. So the first energy level has one subshell, and that subshell is in the shape of an S orbital. So in the second energy level, there are 2 subshells. One subshell in the shape of an S, which is a sphere, and another subshell in the shape of a P. When the energy level is equal to 3, we have 3 subshells: S, P, and D. When the energy level equals 4, we've got 4 subshells: S, P, D, F. Same thing for n equals 4 and n equals 5. Later, it just starts to go a bit like a triangle. A bit. Anyways, last time we talked about, let's see if I can find a slide. Yep, this one. The max electron in an S orbital is 2. Max electron in a P orbital, 6. Maximum electron in a D orbital, 10. Maximum electron in an F orbital, 14. So now that we know these, here are a few rules that you have to follow when doing electron configuration. Always, when assigning your electrons, you might know what that is. You might not know what that is right now, but it'll be clear in a sec. So when assigning electrons, make sure to start from the bottom up. Don't always expect, and second, don't always expect well, each of your orbitals to be filled with electrons. These are the two that I feel is most important. Like, there are a whole lot of rules, but these two, well, I feel they're pretty important. So I'm gonna state them. There are other like not so important rules that I'll go over right now. So I've left myself some beautiful space to do electron configuration. As you can see, I've got part of the periodic table. I have not included the actinides or the lanthanides, which actually are below here, but like I cut them out. So it's just part of the periodic table. That's all we're gonna need. And these are this is the like electron configuration chart thingy. Okay, so here's the cool thing. Basically, we start from 1s right here. So we write down 1s. So this is the first like orbital. Well, yeah, that's nucleus. This is the first orbital. One subshell only. So this one's gonna be 1s. Now we go here. We follow the arrows always. So now we go to 2s. Now we're already moving on to the second energy shell, which has two subshells, 2s and 2p. Basically, one of these subshells is shaped like an S, the other one's shaped like a P. So now we go to P, 3s, 3p. But here, note, follow the arrows. Instead of going to 3d, which we are going to if we follow like that, we are going to go to 4s. So we always follow the arrow. And then after that, we go follow the arrow back again. So we just basically just follow the arrow. We do not go like this. This is wrong. We go like this. Like just follow the arrow and just go, well, sideways down. Okay. Basically, now we're gonna start assigning electrons. So for a atom like hydrogen, it only has one electron normally, okay? So first of all, the first thing we're gonna do is to figure out how many electrons. So if I say hydrogen minus, originally hydrogen has one electron to balance out the one proton positive charge. But now minus means it's -1, like the charge. So it gained one electron. So like totally it's got 2 electrons. So first of all, we've got to figure out how many electrons it has due to the, well, what did I say due to? Like, from the charge and also the element itself. Now these are the orbitals that we've written out in like, well, not graph form. Now, like I said, we start assigning electrons. We start from the bottom like level, which is gonna be 1s. And when we assign electrons is, we know that an s orbital can hold a maximum of 2 electrons, p orbital 6 electrons, d orbital 10, and f orbital 14 electrons. So let's start assigning them. 1s, the first shell on the first subshell on the first energy level, that is in the shape of an s orbital, can take 2 electrons. The second energy level, the first shell on the second energy level, also in an S shape, can take 2 electrons. Now the second subshell on the second energy level, which is in the shape of P, can take 6 electrons. Of course, now I have not declared which element I'm doing this electron configuration for, and yes, every single element have a different electron configuration, but, well, let's try to figure out which element after I finish assigning the electrons. Technically, you could write everything out. Well, now this one's going to be 0. And 3s, 1. 3s has a maximum of 2, but we only need 1 electron. We don't need to fill the whole shell, the whole orbital up, so 1 electron. For anything with like 0 electrons, we can scratch that, which means that this is our electron configuration. Now let's try to figure out which atom this electron configuration is for, assuming the atom is neutral. You will know why this assumption is very important in a sec. So now, let's take a look at this. 2 electrons here, 2 electrons here, 4 electrons total, 6 electrons here, 10 electrons total, 11 electrons total. So if the element is neutral, 11 electrons, which gives you a negative 11 charge, will have to be balanced with a positive 11 charge to give you a neutral element. Oops. Again, I have pressed the button. I am so very sorry. Okay, so negative 11 charge has to be balanced by positive 11 charge, which is the only way to give you like a neutral atom. So assuming this atom is neutral, each proton has 1 positive charge. 11 positive charge means 11 protons. And if we go to the 11 atom, the atom with an atomic number of 11, number of protons of 11, it is sodium. So that is what our electron configuration is for. Now let's try to do an electron configuration for aluminum, which has 13 electrons. So again, let's start writing the basic structure. 1s, 2s, 2p, 3s, 3p, and maybe 4s. So 1s2, 2s2, we're assigning electrons now. 2p6, since these shells are all going to be filled up, we're going to assign the maximum amount of electrons it can hold. 2, 6. Now let's add these. So this is already 10, 12. Okay, so it's 3p1, and then we scratch the 4s. Check to see if it's correct. 10, 2 plus 1 is 3, 13, aluminum. Neutral aluminum. Now let's try electron configuration for arsenic. As. It's like a poison. 2 minus. Let's start from 1s2, 2s2, 2p6, 3s2. I prefer to write down the number as I go along, so I don't have to erase anything afterwards, but like the most foolproof way is to first write down the basic structure. Yeah. 3p6, 4s2. We're going along the arrow. 3d. I'm not sure if we need the 10. First of all, arsenic 2 minus. Arsenic will normally give you like 33 electrons. A neutral arsenic atom. 2 minus, it gains 2 electrons, so it's going to be like 35 electrons. 10, 20, 30. After the 3d, we go to 4p. 4p5. Notice that the 4p, like the p orbital on the 4th energy shell, well, on the 4th energy level, I should say, it's not filled because we don't have that much electrons. So basically, that is the electron configuration for arsenic. Well, 2 minus. Now, this is like, if we're doing an electron configuration for something like, well, I don't know, a very heavy element, francium. This is gonna be super long. And I would not like to see for example, a question asking you to do electron configuration for francium, long-handed way. Humans have invented another shorter-handed way, which is, in my opinion, like so much shorter and so much more convenient. Doing an electron configuration for francium will probably cause you to go all the way over like here. Well, yeah, it will go all the way over here. And basically, it's gonna be hard. But of course, it's not that complicated, but still complicated. Let me just refresh everything here. There you go. That's why people have invented a new way of doing this called the noble gas notation. We know that the noble gas is very stable. Like, they're the most stable elements. Which means that if they're stable, can't we, well, they must have filled up energy shells. So can't we borrow their structure into our electron configuration for things that are not as stable? The answer is we can't. So we can borrow their structure. So technically, say a noble gas, so like a long-handed like electron configuration for neon. Oops, didn't mean to press that. For neon is, let's see, 10 electrons. 1s2, 2s2, 2p6, and there we go. Now we can change this thing straight into neon in like brackets, square brackets. This thing means that we just shortened a lot. Now, we don't have to use neon. We can use helium, for example, if we're doing a configuration for lithium. The most convenient way, for example, if you're doing francium, you can also use helium, like helium, and then everything else. But it's not going to be convenient, right? So the way that I found that is, well, the conventional way of, not I found, well, it makes sense. So, the most convenient way is to just use the noble gas that is one row above the element that you're trying to do. For example, if I'm doing barium, and then if I use helium, wow, that isn't much difference from like the long-handed electron configuration. But for barium, what if we try to use radon? Yeah, radon. Then we found that barium has 56 electrons while radon has 86. So just this has more electrons than barium. It's not gonna work. That's why we always go to like be most convenient, we always go one row above. If we go in the same row, well, too much electrons for the noble gas. If we go like too many rows above, it's not convenient. So we always go one row above. And in this case, we use xenon, taking care of 54 electrons. Barium has 56 electrons. 56 minus 54 gives you 2. So 2 electrons that we still need to add here afterwards. That makes it a whole lot more convenient, but here's the thing that you've got to be wary of when adding the extra 2 electrons. Do not start from 1s. Because as we can see, barium is on the 6th energy level. Basically, xenon took care of all the core electrons. So we only need to add on the valence electrons. Like the valence, remember, is the electrons on the outermost shell. But sometimes, for example, when we're like going back, we still need to add a bit of core electrons. But mostly, it's going to be valence electrons. So we start from the 6 here. N equals 6. This one. Of course, the reason for that is because the electrons are basically valence. So 6s2, and that is our noble gas electron configuration for barium. If we try to do a long-handed electron configuration, it's going to be long. Well, yes, not that long, but it's not going to be convenient. That's why the noble gas notation is invented. And again, to summarize, basically what we're doing is that we're just borrowing a noble gas like structure and using it in our electron configuration. Well, so that's everything you need to know for 6th grade chemistry for electron configurations. You might go like, well, why is this useful? But later when we're trying to figure out valence, and also when you're trying to figure out like reactions and stuff, this can be very useful. Again, this might not be a lot of fun. This specific part might be a bit boring, but later you will see how this one pays off. So that's all for today, and see you next time.